Ever wondered why your phone's AI sometimes mistakes a cat for a dog? Or why a self-driving car might misread a stop sign? The answer lies in label noise, those hidden errors in training data that trip up even the most advanced neural networks. Today, we're unpacking a groundbreaking study that reveals how these systems process mistakes, and why some of our best tools for fixing them are rooted in a two-stage learning process. Let's dive deep. Let's start with the basics. Neural networks are like superpowered students, learning patterns from data, images, text, sounds. But what if their textbook has wrong answers? That's label noise. Imagine a math student trying to learn algebra with half the solutions in the back of the book incorrect. They'd get confused, right? This study shows neural networks do the same, but with a surprising, predictable pattern. The key insight: when faced with noisy labels, neural networks go through two distinct stages of learning. Stage 1, the signal learner. In the first phase, the network focuses on clean data, the correct labels. It's like a student mastering core concepts, ignoring flawed problems. The model learns the signal, the true patterns in the data. This is where it becomes good at generalizing, applying knowledge to new examples. But here's the twist: the network actively ignores noisy samples. Why? Because errors don't align with the data's underlying structure. Think of it as the student spotting a typo in a problem and moving on. Mathematically, this happens because noisy examples tend to have higher loss, a metric measuring prediction error. The network prioritizes minimizing loss on clean data, effectively filtering out noise. Stage 2, the noise trap. Now things get tricky. If training continues too long, the network starts memorizing errors instead of real patterns. It's like the student giving up on math and just copying wrong answers. This leads to overfitting. The model performs well on training data but fails in real-world scenarios. The study tested this with a two-layer neural network using synthetic data, where errors were controlled, and real-world datasets like CIFAR10. And guess what? The two-stage pattern held up every time, confirming that this isn't just theory. So why does this matter? Two common techniques for handling label noise, early stopping and sample selection, are actually explained by this process. Early stopping works because halting training at the end of stage 1 prevents the model from entering the noise trap. It's like stopping the student before they start copying wrong answers. Sample selection relies on the fact that clean data points have lower loss. By focusing on these, the model avoids noise, a strategy known as loss-based filtering. This isn't just theory, it's practical. For example, a medical AI trained on noisy patient data might start associating rare conditions with entirely the wrong symptoms. But with these insights, we can build systems that filter out noise, making AI more reliable in critical fields like healthcare, self-driving cars, and virtual assistants. Understanding this two-stage process isn't just about fixing errors, it's about rethinking how we design AI. By aligning training strategies with how neural networks naturally process noise, we're one step closer to systems that learn smarter, not just harder. Thanks for watching, stay curious, and let's keep pushing the boundaries of what AI can achieve.